Example 2, solve y double prime minus 2xy prime plus y equals 0. Solution. We assume there is a solution of the form y equals the sum from n equals 0 to infinity of c sub n times x to the power n. Then y prime equals a sum from n equals 1 to infinity times n to the power c sub n times x to the power n minus 1, and y double prime equals the sum from n equals 2 to infinity of n open n minus 1 close c sub n times x to the power n minus 2 equals the sum from n equals 0 to infinity of open n plus 2 close open n plus 1 close times c sub n plus 2 times x to the power n. As in example 1, substituting in the differential equation, we get the sum from n equals 0 to infinity of open n plus 2 close open n plus 1 close c sub n plus 2 times x to the power n minus 2x times the sum from n equals 1 to infinity times n times c sub n times x to the power n minus 1 plus the sum from n equals 0 to infinity of c sub n times x to the power n equals 0. The sum from n equals 0 to infinity of open n plus 2 close open n plus 1 close times c sub n plus 2 times x to the power n minus the sum from n equals 1 to infinity times 2 n times c sub n times x to the power n plus the sum from n equals 0 to infinity times c sub n times the x to the power n equals 0. The sum from n equals 0 to infinity of open bracket open n plus 2 close open n plus 1 close times c sub n plus 2 minus open 2n minus 1 close c sub n open bracket x to the power n equals 0. This equation is true if the coefficients of x to the power n are 0. Open n plus 2 close open n plus 1 close c sub n plus 2 minus open 2n minus 1 close c sub n equals 0. Sidebar. The sum from n equals 1 to infinity of 2n c sub n times x to the power n equals the sum from n equals 1 to infinity of 2n times c sub n times x to the power n. Back to the text. Equation 7. C sub n plus 2 equals 2n minus 1 over open n plus 1 close open n plus 2 close times c sub n equals 0, 1, 2, 3. We solve this recursion relation by putting n equals 0, 1, 2, 3 successively in equation 7. Put n equals 0, c sub 2 equals negative 1 over 1 times 2 times c sub naught. Put n equals 1. Put n equals 1 c sub 3 equals 1 over 2 times 3 times c sub 1. Put n equals 2. C sub 4 equals 3 over 3 times 4 times c sub 2 equals negative 3 over 1 times 2 times 3 times 4 times c sub naught equals negative 3 over 4 factorial c sub naught. Put n equals 3. C sub 5 equals 5 over 4 times 5 times c sub 3 equals 1 times 5 over 2 times 3 times 4 times 5 times c sub 1 equals 1 times 5 over 5 factorial times c sub 1. Put n equals 4. C sub 6 equals 7 over 5 times 6 times c sub 4 equals negative 3 times 7 over 4 factorial times 5 times 6 times c sub naught equals negative 3 times 7 over 6 factorial c sub naught. Put n equals 5. C sub 7 equals 9 over 6 times 7. C sub 5 equals 1 times 5 times 9 over 5 factorial 6 times 7. C sub 1 equals 1 times 5 times 9 over 7 factorial c sub 1. Put n equals 6. C sub 8 equals 11 over 7 times 8. C sub 6 equals negative 3 times 7 times 11 over 8 factorial c sub naught. Put n equals 7. C sub 9 equals 13 over 8 times 9. C sub 7 equals 1 times 5 times 9 times 13 over 9 factorial c sub 1. In general, the even coefficients are given by c sub 2n equals negative 3 times 7 times 11 times ellipsis times open 4n minus 5 close over open 2n close factorial c sub naught, and the odd coefficients are given by c sub 2n plus 1 equals 1 times 5 times 9 times ellipsis times open 4n minus 3 close over 2n plus 1 close factorial c sub 1. The solution is y equals c sub naught plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed plus c sub 4 x to the fourth power plus ellipsis equals c sub naught open 1 minus 1 over 2 factorial x squared minus 3 over 4 factorial x to the fourth power minus 3 times 7 over 6 factorial x to the sixth power minus 3 times 7 times 11 over 8 factorial times x to the eighth power minus ellipsis close plus c sub 1 times open x plus 1 over 3 factorial times x cubed plus 1 times 5 over 5 factorial times x to the fifth power plus 1 times 5 times 9 over 7 factorial times x to the seventh plus 1 times 5 times 9 times 13 over 9 factorial times x to the power 9 plus ellipsis close. Or equation 8, y equals c sub naught open 1 minus 1 over 2 factorial x squared minus the sum from n equals 2 to infinity of 3 times 7 times ellipsis times open 4n minus 5 close over open 2n close factorial times x to the power n close plus c sub 1 open x plus the sum from n equals 1 to infinity of 1 times 5 times 9 times ellipsis times open 4n minus 3 close over open 2n plus 1 close factorial times x to the power 2n plus 1 close. Note 2. In example 2, we had to assume that the differential equation had a series solution, but now we could verify directly that the function given by equation 8 is indeed a solution. Note 3. Unlike the situation of example 1, the power series that arise in the solution of example 2 do not define elementary functions. The functions y sub 1 of x equals 1 minus 1 over 2 factorial x squared minus the sum from n equals 2 to infinity of 3 times 7 times ellipsis times open 4n minus 5 close over open 2n close factorial times x to the power 2n and y sub 2 of x equals x plus the sum from n equals 1 to infinity of 1 times 5 times 9 times ellipsis times open 4n minus 3 close over open 2n plus 1 close factorial times x to the power 2n plus 1 are perfectly good functions, but they can't be expressed in terms of familiar functions. We can use these power series expressions for y sub 1 and y sub 2 to compute approximate values of the functions and even to graph them. Figure 1 shows the first few partial sums, big T sub naught, big T sub 2, big T sub 4, Taylor polynomials for y sub 1 of x, and we see how they converge to y sub 1. In this way, we can graph both y sub 1 and y sub 2 as in figure 2. Note 4. If we were asked to solve the initial value problem, y double prime minus 2xy prime plus y equals 0, y of 0 equals 0, y prime of 0 equals 1. We would observe from theorem 11.10.5 that c sub naught equals y of 0 equals 0, and c sub 1 equals y prime of 0 equals 1. This would simplify the calculations in example 2, since all of the even coefficients would be 0. The solution to the initial value problem is y of x equals x plus the sum from n equals 1 to infinity of 1 times 5 times 9 times ellipsis times open 4n minus 3 close over open 2n plus 1 close factorial times x to the power 2n plus 1. Sidebar figure 1, where big T sub naught and big T sub 10. Then you have figure 2 in the sidebar, which is y sub 1 and y sub 2.